Hello, everyone. It's Mr. Bronze coming at you here on our first day back from the winter break. I hope everyone had a great holiday and a happy new year. We're now in 2021, and 2020 is finally over. Thank goodness. All right. So, what we're going to do, I know it's been a week and a half that you've been out of school. Certainly haven't been thinking about statistics over the course of that time period, I would imagine. So, we're going to go back between today and tomorrow, sort of refresh our memory as to what we were working on before the break, right? Working on some permutations, and we're going to throw in the counting principle today. So what we're going to do is we're going to work through the lesson together as we do a couple of example problems, and then I have a homework assignment for you, also attached in the stream. So with whatever remaining time you have left in the period, you can start that, maybe even finish it. Anything that you don't finish, of course, during the period, you'll finish on your own and submit that today to me by midnight. All right, so let's get going. We're going to talk about the counting principle here. Now, what we're going to do is we're going to open up a little scenario. We talk about probability. Often, some very common examples are used. Things like tossing a fair coin, rolling a fair die, picking a card from a fair deck of cards, that sort of thing. So we'll start with tossing a fair coin. Now, we know as long as the coin is fair, which means it hasn't been manipulated or changed in any way, that the probability of landing on heads or the probability of landing on tails is exactly the same, right? Equal probability. 1 out of 2. You could call it 1/2, call it 50%. You can call it 0.5, whatever you like. So what we're going to talk about now is, let's imagine we had two fair coins and we threw them up in the air and we let them hit the ground, right? And then we look to see, are they heads or tails? Let's figure out a sample space, and we're going to begin by constructing a tree diagram. So I want to kind of refresh your memory again. How do we construct a tree diagram over an event that is occurring and taking a look at the outcomes? So we have to imagine that we've got these two coins, right? Or even we imagine we flip one coin, we look at it, we pick it up, we flip a coin a second time. That would be the same as flipping two coins or tossing two coins at the same time. So looking at the first coin, there's two outcomes. So we start from a point here. I'm going to move from left to right, which is generally how we see tree diagrams drawn for probability. And we know we have two outcomes. So I'm going to put a little text box in here. I'd like you to do the same. Work along with me in your notes on your Chromebook, please. And we are going to go ahead and put these two possibilities in. And as we said earlier in the description in the notes, H for heads, T for tails. So there we go. Our first flip, two possible outcomes. Now, this part of the tree diagram where the first branches end are the possible outcomes. So that represents the first coin. From there, we're going to do it again from each one of these points, because that first coin could have landed heads up. And if it did, and we flipped it again, or we looked at the second coin that we may have flipped at the same time, then we have, once again, two other potential outcomes. They're the same two as before. That second coin could be either a heads or tails up. So look at what we have so far in our tree diagram. We have a pathway, first flip heads, second flip heads, or a second pathway, first flip heads, second flip tails. All right, let's finish out this tree diagram, because we also have to think about and consider what would happen if the first coin was showing tails. Again, we have two possible outcomes, and it's the same two we've been working with the whole time. The possibility of getting heads and the possibility of getting tails. There we are. So that's our whole tree diagram for flipping two fair coins. So now let's list our sample space. And actually what I'd like to do is show you how, when you look at your tree diagram, you can, at the end of every branch, and when we talk about branches, we start on the left. The end of the branch is the rightmost portion of the branch. So this would be the end of one branch. How did we get there? Well, we got a heads on the first coin, heads on the second coin. So we can put our results right there. And let's take a look at the next branch. How did we get to this T? Well, first we had to go through heads on the first coin and then tails on the second. So there's our outcome of flip number 2. And then we go down to flip number 3. How did we get here to the end of this branch? We went tails first, then heads. And then our last, not least, down at the bottom, our fourth and final branch, we had to travel through a T and a T. So both coins were tails. So a lot of times you see students and even teachers, when they construct a tree diagram, at the end of each branch, they'll put the list of outcomes, which represents a list of all the possible outcomes. And remember, our possible outcomes are referred to as the sample space. So if we were asked to put a sample space together, we use squiggly brackets to enclose the entire sample space. And then within those brackets, we list all our outcomes and we put them all in their own sets of parentheses. So there's our first outcome, 2 heads. And then we had, we don't want that. Then we had a head and a tail. And then we followed that up with tails and heads. And finally, tails and tails. And then, of course, we close it up with a squiggly bracket. And this is our, we call, I'm sure there's some sort of specific technical name. I refer to it as a squiggly bracket. If anyone knows the name, you guys can fill me in when I get back in school sometime in the very near future, and then we'll know what they're really called. All right, so what do we see here? Well, we can see that by flipping 2 coins, there's 4 possible outcomes. All right, so we kind of summarize that right here. All right, 4 possible outcomes. Where is my highlighter? There we go. 4 possible outcomes. All right, so now one of the things that we want to understand is we don't always necessarily have to draw a picture. We don't have to use a tree diagram. We don't have to individually list the sample space. Because if you think about that, that wasn't too bad with 2 coins. But what if we flip 3 coins? That's probably manageable. But what about 4 coins? How about 10 coins? Now you start talking about a ridiculously large tree diagram with a large sample space. So we talk about using multiplication as a shortcut to be able to count up the number of outcomes. And this is called the counting principle. So let's add that to our notes. Right? The counting principle. Multiplication really shortens up the process for us. And it's very simple. Again, we're using multiplication here. So here's an official definition of the counting principle. So it states that if one activity can occur in any of A, letter A ways, and then afterwards, second activity can occur in any of B ways, then both activities can occur in that order in A times B. So let's sort of think about how this applies to what we just did with our fair coin. So the first time we flipped the coin, there were 2 possible outcomes, right? Let's get my pen back. There we go. So we had 2 possible outcomes. Then when we flipped the second coin, again, there were 2 possible outcomes. And if we use multiplication, 2 times 2 shows us that in the end, there was a total of 4 possible outcomes, which we already knew because we made our sample space. So we see here, we're going to fill in the blank. We just answered this question. If we had 2 possible outcomes first, and then we had 2 possible outcomes second, we had 2 times 2 equals 4 possible outcomes. There we are. Now, how about we sort of reflect back on what I mentioned a few minutes ago? What if we tossed a fair coin 3 times? How many outcomes would we have? Well, let's use the counting principle. When we toss that first coin, there's two outcomes. The second coin, there's two outcomes. The third coin, there's another two outcomes. And there we are with a total of 8 outcomes. So we see here that multiplication really helps us out. It's a huge time saver. Okay. So one of the things we have to keep in mind, though, and a key to all of this, I'm going to want you to add this word here, is independence. Okay. Independence. And the reason why I want to add this word is our events have to be independent of each other if we're going to use what we call the counting principle. Okay, back again. Sorry, I had to pause for a second there. Okay, so that being said, we have our counting principle. Let's start to talk about how probability works its way into the mix here with this conversation. So we mentioned earlier, if we're going to toss a fair coin, the probability it lands on heads, or tails for that matter, is 1/2, right? Okay, so let's put that in here. Let's fill in the blank. Half. All right, pretty common knowledge there. Now, if we toss a second coin, the outcome is independent. Now, I ask you guys, I want you to think about this for a minute. Why? How can we make a statement like this one here? We've tossed one coin. It's already done, right? Let's say it landed heads up. And now we're about to flip that second coin. The outcome of flipping that second coin, which could be heads or could be tails, is independent of the outcome of the first coin. And why can we say that? That's because these two events have nothing to do with each other. Okay? Absolutely nothing to do with each other. The first coin, whether we get heads or we get tails, does not change the probability of us getting heads or tails on the second coin. So we refer to these events as independent events. One does not affect the other. And as long as our events are independent, we can use the counting principle. So I want to make that very clear right off the bat. Now, because we have independence, or with each example, we're going to make sure we have independence, the events do not affect each other, we're going to be able to use that counting principle with probabilities. Okay, so let's take a quick for example. Let's use, let me put up the screen here, it's a little distracting. There we go. Let's use our 2 flips of the coin. All right, now, when we flipped our first coin, the probability of getting H ahead on the first coin was 1 out of 2. Okay, great. And then we flip the second coin. Probability of getting heads on the second coin. Once again, 1 out of 2, right? So now, knowing what the probability was of each of these 2 separate events, which we've already said are independent of one another, what is the probability of flipping 2 coins and they're both going to be heads? Well, since they're independent, that would mean we can take the probability of getting a head on the first coin and multiplying that by the probability of getting a head on the second coin. We already have those probabilities, right? We just determined those. So if we take 1/2 times 1/2, we find that the probability of flipping 2 coins and having them both land as heads is 1 out of 4. So again, the key with using counting principle, whether we're trying to find the number of different outcomes, which we did initially with the counting principle, or using it in an example like we just completed here with probabilities, the key is the events must be independent. Okay? We're going to talk about later on in our probability unit, what happens if the events are not independent? And then we have a whole another conversation to have about that. But that's not for some time. So with that said, when an event consists of two or more separate events or activities, and that's what we just did. The probability of the event that we just looked at were two separate activities. It was flipping a first coin and then flipping a separate coin. So we have a name for this type of event. We call this a compound event. So as long as we're doing two or more separate things, we've created a compound event. So if we flip a coin and we roll a die, compound event. If we spin a spinner and roll a die, compound event. So I think you guys see where we're going with this. All right, so let's take a look at a good example. So we've got ourselves here, problem number one, where we have a family with 3 children. We're going to let M represent male and F represent female, and assume that the probability of getting either a male or a female child at birth is both 1/2. Okay. So we want to know how many outcomes are in the sample space that shows the sex of the 3 children. Well, let's create a tree diagram. So let's reflect back on what we did a little bit earlier. We said we have to start with the first collection of possible outcomes. And we said with our first child, there's 2 outcomes. We're calling them in this case male and female. So we can have either M or F. So there is baby number 1. Then move on to baby number 2. So I'm going to put out a couple of get my branches drawn first, and then I'll fill them in as long as I can get some cooperation here. And go, and okay. So now we know that regardless of what the first child was, in this case it was a male, we can either have a male or a female for the second child. So let's get a couple more F's here for the females. And baby number 2 down here says, well, if we had a female in the first child, possible outcomes for the second child, again, are male and female. All right, so this is exactly what we had in the opening exercise. Now we're expanding this out because now we're going out to 3 children. So now we're going to get some branches going here. Whoops. Keep doing that. You're a little too close to that letter. We're going to start over here. There we go. Okay. And we'll get some branches going here. And one more time down at the bottom. So you can see this is a bit of a repetitive process, not one that we're entirely unfamiliar with. And now we can begin to fill in all our possible outcomes. And as we said, with each of the branches, regardless of the sex of the first 2 children, whether it be male or female, those 2 options are still on the table for the third child. So, with the technology that we have, we can create a nice, neat tree diagram, and we can see all our possible outcomes here. So let's take a look, and let's go ahead and do a sample set as well. Let's put that over here. So we're going to start with our squiggly brackets and follow the first branch. So we start here all the way at the left. I'm going to travel up this first branch, and I have an M, an M, and an M. 3 male babies. So let's get that in there. M, M, M. Maybe what I'll do, why don't I do this? There we go. Just kind of shorten it up a little bit. And my next branch, I have MMF, right? MMF. Then we go MF, male, female, male. So MFM. And we'll continue down. And now we have MFF. And that's a total of 4 so far, and that takes care of the top half of the tree diagram. Now we're going to go down to the lower half where the firstborn is female. So now we have female, male, male. And after that, we have female, male, female. Oops, close my parentheses. There we go. And then we have female, female, male. And finally, 3 females. And there we are. We have our sample set. And we can clearly see that there are 8 possible outcomes. Had we used the counting principle, hopefully everyone's got all this down. So just, if I haven't mentioned already in the video, to the sub in the room, if we need to pause the video at any time, please feel free to do that. If anyone needs an extra moment. In the counting principle, our first child, we had 2 possible outcomes. Second child was 2 possible outcomes. Third child was 2 possible outcomes. All independent events. So we can verify that, yes, indeed, there's a total of 8 possible outcomes. So part B is interesting. Now we're going to shift gears over to the probability end and say, well, what is the probability that all 3 children are the same sex? So they're all male or all female. Now, could we take the time and construct our tree diagram and then look at our outcomes and see that we have, let's see, we've got 1 here and 1 here. All males, all the same sex, all female. So 2 of the outcomes out of the total of 8 outcomes. So the probability would be 2 times 8. 2 over 8, excuse me. Yes, we can do that. But what if we wanted to use the counting principle? Let's think about this. The probability of all 3 children being the same sex can also be thought about as they are all male or all female. Okay. So let's think about this. Are they independent, male and female? The answer is yes. So if we have an or probability, we can say, okay, well, what's the probability that they're all male? And then we can add to that the probability that they're all female. So now we're starting to get somewhere. So we know that the probability out of the 8 outcomes that they're all male is 1 out of 8. And the probability that they're all female is 1 out of 8. And that gives us 2 out of 8. Or if we put it in simplest form, 1 out of 4. So certainly we're talking about getting all of these together, all the same sex, and having a nice probability of 1/4. So if parents are interested in doing that, not a bad probability, 1 out of 4 chance. All right, and that concludes question 1. We got one more problem to do together, and then we'll let you get going on the homework. So problem number 2, we have 2 fair dice that are rolled, each numbered 1 through 6. So a normal die that we're accustomed to. We're going to find the probability of 3 different scenarios. So let's start with the first one. So the first one says probability the sum of the numbers on the dice is 9. So first of all, let's think about how many total possible outcomes are there when we roll 2 dice, a pair of dice, excuse me. So let's see, when we roll the first die, there's 6 outcomes, and that is independent of the second die, which also has 6 outcomes. So when we multiply them as per the counting principle, 6 times 6 is 36 possible outcomes. Then I put together a little table for you guys to show you. Here we would have the first die on the vertical axis, the second die on the horizontal axis, and we could do any combination of 6 and 1, 5 and 1, 4 and 1, etc. And there are 36 possible boxes. So I'm giving you a little bit of an illustration here, just a different angle of talking about outcomes and possibilities. So where are all the outcomes in this table that sum to 9? Because that first question said, find the probability that the numbers on the 2 on the dice, the 2 dice, adds up to 9. Well, let's see. Well, I can't add 1 and 8 because there's no 8. That doesn't work. 2 and 7, that doesn't work. So the first one, we'll use my little highlighter. The first one is going to be 3 and 6. So I'll fill in that box. So 3 and 5, 3 and 4, those are all too small. How about 4? Well, 4 and 5 is 9. How about 5? Well, 5 plus 4 is 9. And finally 6. 6 plus 3 is 9. So in the illustration of our table, we can see out of the 36 possible outcomes, there are 4 of them that sum to 9. So underneath, I'm going to say there, whoops, carried away with my typing, there are 4 ordered pairs, which we have highlighted the table above. Some of the numbers is 9. And let's go ahead and list them. What were the ones that we highlighted? We highlighted 3 and 6. Also highlighted 4 and 5. We highlighted 5 and 4. And we highlighted 6 and 3. This is a nice little summary here. So let's go ahead and answer our question. We want to know, initially the question said, what's the probability that the sum is 9? Well, how many ways could we make 9? Well, we found 4 different ways out of the total number of outcomes, which is 36. So 4 out of 36. And 4 out of 36 can be simplified to 1 out of 9. So here we have a nice little description as to what we did and the outcomes that satisfied the probability question. Sum is 9. There were 4 of them out of our total of 36. All right, let's move on to part B. So part B, here we want to know, what is the probability that when we roll the pair of dice, that we get at least 1 4? All right, so we're going to highlight again. So let's see. So if we start here with this 4, we could have a 4 and a 1. That gives us a 4. Or we could have a 4 and a 2. That gives us a 4. A 4 and a 3, a 4 and a 4, a 4 and a 5, a 4 and a 6. So we get to highlight every outcome in this row where 4 is one of our 2 dies. Now don't forget though, we also have 4 on the other die as well. It says at least 1, could be 2. So certainly these values here all would satisfy our condition of having at least 1 4. It could either be on the first die, represented here on our left vertical axis, or on the second die, on our bottom horizontal axis. So what did we get as a total here? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, so let's put this all together. Just like before, a little summary, there are 11 ordered pairs highlighted in the table in which at least one die shows a 4. So that means a probability of at least 1 4. So that 11 possible outcomes out of the total of 36. There we are, probability 11 over 36. All right, last one. Now, what's different about part C from our first couple of parts A and B, is this word right here, and. So and makes probability somewhat tricky. Oops, lost my page here. Let me go back. Oh, getting all sorts carried. There we are. Okay. So and kind of gums up the works a little bit. So what we need to do is when we think about ands, we want to think about intersection, because we want to satisfy both parts of the criteria of this probability. So when we see and, we want to think about intersection. So let's first highlight all the numbers that sum to 9. We did that earlier, right? So let's pick yellow. So let's see, we said 6 plus 3, that was 9. 5 plus 4, 4 plus 5, and 3 plus 6. We had 4 of those. Okay. And then now for at least one 4, we're going to use the blue. So we found that this whole row of 4s was good. And we also said that this whole column of 4s is good. All right. So now that we've highlighted everything, what we want to do is we want to say, okay, for our two different conditions, sum of 9 and at least one 4, where do they intersect? And we find that with only 2 ordered pairs that have both colors of our highlighting, so that satisfy both conditions, the sum of 9 and at least one 4. So let's put this in a nice summary sentence. We say there are 2 ordered pairs that meet both criteria. And let's put our probability together. We say we have the probability of the sum of 9 and at least one 4. And what we found through using our table was 2 outcomes out of the total of 36. And if we wanted to simplify that fraction, 1 out of 18. All right, so that does it for our lesson for today. A little review of the counting principle and then applying it for some probability. So we have a homework assignment attached in the stream for you guys. You can start on that now with whatever time is left in the period. And then again, finish that, submit that to me by midnight tonight. Just real quick, Mrs. Bronze is recovering nicely, although it is moving along rather slowly. Odds are you are not going to see me until next week on Monday, unless some minor miracle happens and she gets a lot better a lot sooner. So that's the basic plan right now. I do apologize. I was hoping to be back today, but I will try to make videos for each day this week and keep you guys up to speed as we're rolling through everything. So, of course, as always, if you need to reach out to me, you can do so in the stream or send me an email. All right, that's it for today. Have a great day, folks, and we'll talk to you tomorrow. Bye-bye.